Here we're going to talk about Monero, especially addresses and staff addresses. And we're going to deep dive into the specifications and take a close look at the protocol. I linked the specifications of Monero in the video description, as well as a collection of Python code that calculates everything you see here, so you can test it out with own transactions that you made in the wild. We will start by recapping some basics of asymmetric cryptography and then go over to addresses and staff addresses. Have fun. All right. As you can see here, the blue line is an elliptic curve. And in asymmetric cryptography, you need something like a one-way function, a function that is easy to calculate in the one direction and difficult to calculate in the other direction. In this case, this is point addition on an elliptic curve. So if you do have a point G, which could be here, and you say something like G plus G, which would be a point P. In the graphical representation, this would be something like this. And point here is here. It's easy to calculate P, but it's difficult to calculate back to G. This is the theory. More generally written, you can write K times G. So if the base point G is added K times to itself. And this K is the private key, how many times the base point is added to itself. And this P is the public key. So that's basically it. G is publicly known, so an observer knows G, but he's unable to recalculate K if he's only if he was only able to capture P. Good. Let's see how this works with a quick example. How this is used to generate a shared secret. As usual, we have Alice. Alice and Bob. And both generate two keys. They generate a private key. Convention is private keys are written lowercase, public keys are written uppercase. And they calculate A, the public key, with AG. And Bob is doing the same thing. He generates a B and calculates uppercase B with BG. Okay, they both exchange their public keys as usual in the Diffie-Hellman key exchange. Bob sends B, Alice sends A. And Bob calculates something like BA, which is BAG. And Alice is calculating something like AB, which is the same as ABG. And this is the shared secret. If an observer, I think he's called Charlie in the middle, captured those public keys, he's unable to calculate the shared secret. First of all, let's define the scope of this video. We're trying to understand what is a staff address. We're trying to understand what is a transaction public key, which is the staff address. And we're trying to understand why Bob generates a view key and why he generates a span key, and how both keys are used to unlock a transaction or to notice if someone sent money to Bob. We also will understand why Bob's raw address, which he initially sent to Alice, never occurs in the blockchain. And we will understand why the addresses that occurs in the blockchain, the staff addresses, are always different, and why Bob don't have to generate new addresses like in Bitcoin or something like this each time. Okay, but we will make this step by step. So we start first with Bob. Alice wants to send Bob one Monero, and Bob starts by generating an address. He generates a private key, a private view key. Wait, we will start with a span key because it's the private view key is usually derived from the private span key, but this doesn't matter in this case. So he generates a private span key, and he also calculates a public span key, which is B, and he generates or derives a private view key. Important if you derive it from a span key is that it's not able to calculate it backwards. It's just able to, it's a one-way function like a hash function. And he also calculates public keys. Times G, like we saw above in the example of elliptic curve cryptography. Okay, he after that he takes both keys, both public keys, the view key and the span key. And then he does some encoding, checksumming, and versioning, and so he generates an address and sends this address to Alice. So this is basically the address, or raw address. Raw address. And this is the address that never occurs in the blockchain. And next we see why. If Alice received this address, she starts and wants to make a transaction to Bob. She starts with generating a random, we call it R, and she generates a public key of this random, which is RG. Okay, and next we will see why she's doing this, and I will write a formula down, and don't understand it immediately. We will come back to this later. So the one time K, this K is basically the public key of the transaction. It's a one-time key, and you will see why, because here's a hash function, and the hash function is calculated by R times the public view key times G, times G, and plus public span key of Bob. Okay, let's start at the formula. First, this is the transaction public key. It's a one-time key. It differs each time, and it's the same thing as the staff address. So the staff address is basically the one-time public key of a transaction. Because a random is involved, it differs each time, and that's exactly the reason why you cannot use Bob's public span key as a transaction key, because it would be the same and would be easily linkable to Bob's raw address here. Okay, now we understood why we brought in the random. Next, why this whole thing here? It has two purposes. The first thing is Bob wants to check if he received a new transaction. So he wants to get the public transaction key, and he calculates something, and he checks if this transaction belongs to him. And the second thing is that the corresponding private key to this public transaction key has to be calculated in a way that only Bob, the owner of the private span key, is able to calculate it. And yeah, how this is possible, we will see in the next steps. So Alice builds a transaction. She takes the one-time public key, the staff address. She takes uppercase R and a few other things that we are going to look at later. Now she sends it to the blockchain. Just write some blocks down. And Bob is repeatedly checking each block and do some calculations. And at these calculations, we are going to look next. So first, he takes his private view key and generates and calculates private view key times R. And this is the same thing as KB RG. Okay, I will mark two things for you. Wait, let's make it green. This is exactly the same thing. Remember, this is exactly, basically this is a public key exchange between Alice and Bob and generating a shared secret. Bob sent his view key and Alice sent uppercase R, the random public key, basically. And what they're doing here is they are doing this calculation to generate a shared secret. And why they do this, you will see in the next step, because if you do some algebra on this formula here, you can write it like a new KSB, a new public send key, and K0 So, and since this and this here is the same, you can check if your own public key is equal to this calculated public key. And this, if this is the case, you know, oh well, I received a transaction. Okay, this is cool, and this answered the first purpose of this formula: how to make sure that the owner of a private key is able to see if he received a transaction. The second thing we want to calculate is how to calculate the private transaction key, the one-time key. For this, I will do some algebraic notation as well. I will write the formula down again. And this is the same as okay, as you can see here, G is in both parts. And what looks like a simple distributive law, but only Bob is able to do this because only Bob is able to split the private view key and G. It's something like this. Oh, well, I have to go down a little bit. So this looks easy, but only Bob is able to do this because only Bob is able to split here the view key, the private key of G. No one else is able to do this. And this part here is, by definition of a public key, the corresponding private key. And that's the way, yeah, we calculate the private key, and only Bob is able to do this because of this part here and splitting this. And yeah, how we are going to use this private key to spend the received output, that's a question we are going to focus on in the next videos. Thanks.